Hello and welcome to Lecture 6, where we begin to go into the details of the IPOP architecture. So last time we saw, from the application's perspective, IPOP is essentially not visible by clients and servers. And once we start zooming in into how IPOP provides the functionality necessary for virtualization, it is implemented as two major modules. We call the TinCan module responsible for handling packets and forwarding packets, and the controller module deals with the connection policies and overlay routing. So these modules are typically run as user-level processes on the same host, the same endpoint, and they provide a level of separation of concerns. TinCan has a data path for handling packets and forwarding them. In the typical case, a packet goes from one TinCan endpoint to another TinCan endpoint without involving a controller. And the controller is responsible for selecting who to connect to, what IP addresses to use, how to map IP addresses, and potentially routing over multiple hops. So this organization is somewhat inspired by OpenFlow's controller architecture, but it's not the same API and it's not exactly the same approach to controllers. In IPOP, every endpoint has its own controllers, and controllers are inherently distributed in this architecture, decentralized. So here we have an application, again blowing up our previous figure, IPOP as a set of two separate modules can be further subdivided on the TinCan side into one module that deals with packet handling, and one module that deals with just a low-level interface to the virtual network device or the TAP device. So an application again uses the socket API using the virtual network interface. IPOP is able to read from this network interface, and TinCan handles this thread, for example, by forwarding to a remote service, or if it doesn't know what to do with this message, it's going to send it up to the controller to deal with it. And packets that are received come from the physical network interface and are handled by IPOP and eventually delivered back into the virtual network interface into an application. Now, we rely on external services to deal with discovery of peers and notification of peers, and that's the online social network service that I mentioned in a previous lecture, and that uses the XMPP protocol for communication. We also rely on stun and turn services for net traversal. Stun provides a reflection service, so allows a node to determine what is the address at the edge of its network address translator. And for most nets, for nets that are of the cone type, as we'll see later, it's possible to do net traversal just by using this stun service. But some nets will not allow hole punching, and you need an external relay, and the turn protocol and the turn server provide that functionality. So the online social network holds friendships, so holds relationships between nodes, essentially allows a node here to discover who they want to connect with. So that can be, again, a public service, for example, a Jabber service maintained by yourself, or it could be a public service like a Google account and the relationships you have with friends that you establish in Google. So how this interface works, how this server behaves, it's beyond the concern of IPOP. What IPOP concerns with is that there's a server that can use the XMPP protocol to discover who are friends or who should be connected with this machine, and to exchange messages with these endpoints. So IPOP in the configuration tells us which server to connect and how to authenticate with that server with a username and password, and it uses that to send a presence message to other nodes in the network to say that, hey, I just joined the network. IPOP also uses stun and turn services to discover endpoints for net traversal, and this is largely done by the libdjango library that IPOP reuses. We do have in the configuration file the ability to name all the stun services you may want to use, or turn services that you may want to use. The XMPP service is also used not only to describe, to tell other nodes that you've joined the network, but also to ask nodes to connect to you. For example, if two endpoints join the network, they may or may not want to create a connection right away. They may only create a connection eventually when they begin to communicate over the virtual network. So the XMPP service is used to send a so-called connection request, and that tells, as we'll see later, what is the endpoint that you're listening and what is the node that you're trying to connect to, and also has information for VPN security establishment. So how does, on the side of the application and packet handling, how does information flow through this architecture? So an application, again, if it's sending a packet, it's going to use the socket API to send a message, and that's going to be on this virtual network interface, this tap device. IPOP itself can read from this tap device using a system call, a read system call. And then it goes into a buffer in the IPOP tap, in one of the IPOP tap threads, a send thread. Eventually this is sent to TinCan through the send function, and TinCan is going to handle this packet from that point on. That typically will mean that a packet is destined to another if the address that the application is sending to corresponds to another node on the IPOP network. This eventually will encapsulate the message, encrypt, determine which link to send it out to, and eventually use the socket API to send over the physical network across the internet to the other endpoint. On the receiving side, the packet comes from the physical network, and it is handled by TinCan, which decrypts the packet, decapsulates the packet, and puts it in the receive queue in the IPOP tap module. The IPOP tap module will get this packet and push it into the tap interface using the write system call, and eventually the application receives that through the socket API. Again, the application is unaware of all that's happening here behind the scenes. The only thing that it interacts with is this tap device. How is this system implemented? These modules are implemented, again, as two separate processes. They're in fact two separate programs. TinCan is written in C++. It builds upon the libdjango library, and C++ bindings are the best way to go. It also uses C for interacting with a low-level tap device. Libdjango actually provides a framework for tunneling over the internet. It's typically used for video and voice, for example, for Hangouts. In IPOP, we essentially use libdjango as a carrier for IP traffic in general. So a lot of the heavy lifting that needs to be done for dealing with net traversal, for interacting with the XMPP service, are actually leveraged by us using the libdjango library. And that's encapsulated in the TinCan module, which essentially can think of as a wrapper around libdjango that does the IP over P2P core data path that IPOP implements. And then the separate module is the controller. Now, the controller itself can be written in a different language. It communicates with TinCan using an RPC-based API, and typically we use Python, and the controller is significantly simpler and smaller than the TinCan module. And we expect most of the developers to focus most of their developer time in the controller policies and implementations, and not much on the TinCan side. The two examples of controllers that we have implemented in our project are the group VPN, which allows you to create essentially clusters where all nodes are connected to all other nodes and IP addresses are not translated. Social VPN is intended for people to connect to friends, and it sets up a unstructured network where every user has their own view of the virtual network and maps other users through dynamic IP address mapping to a local virtual subnet.